Make sure to keep in mind that we're transferring electrons when we're forming ions. That's going to be very important for us in the next chapter when we're making compounds for things, because an ionic compound will have a positive ion and a negative ion, but they have to be the correct charges in order for those ions to be stable. And you have to have the correct number of each ion for the compound overall to be neutral for everything to work out. So we'll continue on that, along that line in chapter 3. Let's talk about mass right now, though. Atomic mass is the relative mass of an atom. So the unit AMU is the one we see most commonly, the atomic mass unit. The Dalton is the same thing. People dealing with proteins and nucleic acids and things like that tend to use Daltons as the unit for it. You remember Dalton from the atomic theory, so it's reasonable that a unit of atomic mass is named after him. But in chemistry, for whatever reason, we still use the generic atomic mass unit, but it's all the same thing. Okay? So here's the definition of an atomic mass unit. 12 atomic mass units, by definition and exactly, is the mass of one carbon-12 atom. And let's be careful about what that means. Carbon-12 is the mass number. That 12 is the mass number. It's the number of protons plus the number of what? Neutrons. It's a count of the massive particles. So mass number is always an exact number. There are no partial protons or neutrons or anything. So a carbon-12 atom with 6 protons and 6 neutrons in it, that's carbon-12. By definition, that is 12 AMU in atomic mass units. So what is approximately the mass of one proton then? Yeah, 1 AMU. Not exactly, because a proton and a neutron are a little different. Okay? But we can say proton approximately equals neutron, approximately equals, but not exactly. Okay. But the true definition, okay, of the atomic mass unit is essentially 1/12 the mass of a carbon-12. Okay? So a mass somewhere in between a proton and a neutron. In fact, it would be the average mass of a proton and a neutron if you did that math right. Okay? So atomic mass can be measured. The mass of any other atom that's not a carbon-12 atom will be given relative to this definition. So this is the only exact atomic mass there is. Everything else will be a measurement, okay, with however many decimal places or sig figs our measurement allows us for, but it'll be relative to that definition there. So it can be measured through mass spectrometry. That's something that measures the mass-to-charge ratio of particles deflected by a magnetic field. We talked about mass-to-charge ratio just a little bit when we were talking about electrons, how they didn't discover alone their mass or their charge, but rather that ratio, because that's what influences how something is deflected by a field. So that we can measure in a mass spectrometer if we have ways to make sure that something gets a single charge. For instance, if it has a single electron added to it or a single electron removed from it, then we can know the mass of any of those particles. Okay? So we can get very accurate masses of samples of elements through a mass spectrometer. It's a fairly sophisticated piece of engineering, but it operates under a pretty simple principle that if we have a vaporized sample, it has to be in a gas phase in order for individual atoms to be affected by a magnetic field. Okay? So we have an electron beam that ionizes the sample. We'll talk about how that works a little bit later on when we talk about ionization energy. Okay? but we will either add an electron or remove an electron from an atom. So now it's an ion, and that ion can be influenced by an electric field or a magnetic field, pretty much the same thing, but that can accelerate the particle, so it sends it shooting through here. Okay? It's got these two electromagnets perpendicular to it, whose magnetic field can be varied, and that diverts the trajectory of these beams, okay, either further this way or further that way, and the relationship between that magnetic field and when you see something at the detector over on that other end, that's what can allow you to determine mass to charge ratio, or just mass, okay, if you know it's single charge for those individual atoms. So let me show you a sample mass spectrum. If we have a sample of natural neon, and all the other noble gases can be separated just from breathing air, usually by condensing it and then allowing the different gases to boil off at different temperatures. Okay? But what we'll have here, this is called a mass spectrum. It's pretty much the result of that mass spectrometer there. So you end up with this graph. The y-axis is fractional abundance. Okay? That means how much, it's relative to how many atoms struck the detector. Okay? And down on the x-axis, okay, m over z, mass to charge ratio. And again, like I said, if we carefully tune that ionization so that only one charge happens, then mass to charge ratio equals mass. Okay? So if we have mass down on the x-axis and abundance over on the y-axis, a mass spectrum of neon would look something like this. You'd see a big peak at 20. Okay, so draw a big line like that. Okay. Its value, its abundance, would be 0.9051. Okay. This is a scale from 0 to 1, usually. Okay. Tiny little peak at 21, okay, 0.0029. Slightly bigger peak at 22, okay, 0.0922. So what this mass detector is showing us, if we put a naturally occurring sample of neon in it, this is showing us the three isotopes, three natural isotopes of neon. Okay. And these may or may not exactly add up to 1. It depends on how it's calibrated and if there is any other little peaks there. Okay? But what this is pretty much telling us is that down here, okay, these masses, these end up being the mass numbers, or very close to the mass numbers of isotopes. Okay? Depending on the instrument, you're able to get those exact masses out to many, many, many decimal places. Okay? It will look like it's very close to 20, but again, the only exact mass measurement is this 12 AMU from carbon. Okay? So if we make a little table out of that information, there, the three isotopes, okay, neon 20, neon 21, neon 22, those are the three ones I had. Yep. Okay. Their atomic mass, okay. Notice they're not exactly the same as the mass number. Okay. This is again relative to carbon-12, and because the proton and the neutron are slightly different, okay, the ratio will alter the exact atomic mass. And then also there are other particles and other weird things that happen that make the exact atomic mass a little bit different. Okay? But there are those. And then their abundance is its proportion, essentially, out of 1 for each of those isotopes. Okay? So what actually happens is we use these abundances to weight those three atomic masses. Okay? So if we take each of those masses and multiply them by their fractional abundance, right? That's out of 1. Okay? Essentially, an abundance of 0.9051 means 90.51%. Okay? So it's just like a percent out of 1. All right. So if you do a little bit of number crunching here, let me tell you what these are. 18.0948, okay? 0.056684, 2.02757. Okay. So then what we do is add those all up. Sum of those is 20.18 AMU, which I've rounded here. This value here, that is the weighted average atomic mass of neon's natural isotopes. Okay. So a natural sample of neon will be made up of these three isotopes in these proportions. Okay. So to make a weighted average of anything that you have with a certain value and a certain amount of that, you multiply the abundance by the value. So some of you may have had a class where grades are weighted in that same way. That works the same way, calculating in a grade book if exams are worth 20% of the grade and homework is worth 5% of the grade and stuff like that. You do that the exact same type of calculation. So let's look at our periodic table. Notice our weighted average here was 20.18. If we look at a periodic table, right there is 20.18. Okay? That shows up on the periodic table. Okay? Okay. It's sometimes called atomic weight. Even though it's a mass, not a weight. Perhaps because it's a weighted average, maybe that makes it a little bit okay to call it an atomic weight. But that lower number on the periodic table, among other things, is the weighted average atomic mass of all of the natural isotopes. So just before we go, I want you to have just a quick look at the periodic table right here. We notice, I told you before that carbon has carbon 12, 13, and 14. But if the weighted average is 12.01, what does that tell you about the relative amounts of these? Yeah, very small amounts of 13 and 14, almost completely carbon 12. Okay. Sodium really only has one isotope, sodium 23. Okay. There are only two isotopes of uranium, 120. No, it's two. It's 126 and 128. Here, we'll talk about that next time, but we can tell something about the abundances of relative isotopes just based off of those values. So that's what we'll talk about next time. Talk about the mole just a little bit, and then we're on to chapter 3.